Hi, guys. How you guys doing this morning?
Pretty good.
Good. Don't forget, we have a quiz today. The quiz opens up at noon. This is our second to last quiz of the semester. Very exciting. And today we're going to start chapter 2.2. I'm going to basically kind of jump right in so that we have plenty of time to cover it. And then see if we have time at the end. I can answer questions. I think yesterday we answered a lot of questions about the homework too. So I want to make sure we get to chapter 2.2 today. Have plenty of time for it. Okay. Oops. There. All right. How many of you guys are taking Calc 2 next semester? I think probably most of you, right? I think it's in the your required courses for your degrees, right? Okay. Alrighty. Yeah, Calc 2 is a lot of fun. I think Calc 2 is it's like all over the map in terms of like the type of topics that we cover in Calc 2, but it's a fun class and interesting. There are a lot of really neat things to cover, topics to cover in that class, but it's very diverse in terms of its topics, you know, but forms a good basis for a lot of other courses that you'll need. Anyway, okay, guys, I am going to start with chapter 2.2. Oops, chapter 2.2. So let me write down what it is and then 2.3. I'm thinking of the next chapter. 2.3. So prelude to definite integral. Okay, so remember our definite integral goes from a to b of f of x, right? So let me get this in focus here. There. So we're going to talk, this is 2.2. We're going to talk today about sort of background information that you need conceptually in order to think about like what's our definite integral doing and what are we trying to do. Okay, so we're going to take a step back. We've been talking about how do we actually take the integral and how do we do it, but now we want to take a step back and think about the definite integral, which is going from point A to point B on some kind of a curve. And what does it actually mean? What is it that we're actually trying to do? So when we try to do the definite integral from A to B, right, we're taking a look at essentially calculating an area between our function and the x-axis. Okay, we're talking about positive areas right now. Okay, we're going to deal with negative areas, you know, in later chapters. So right now we're talking about positive areas. So between the function and the curve, we want to find out what that area is, right? So before we just jump right in and tell you like this is how you do it and whatever, we're going to talk about like what it means and what it is that we're trying to do. Okay, so today we're going to be approximating and computing the area basically between our function and the x-axis. So to do this, we're going to look at velocity as an example. We're going to look at 3 different cases in our velocity. One where we have constant velocity across all time intervals. The next one is where velocity changes from time interval to time interval. And then the last one is where we have velocity is changing continuously. right? So this is a discrete change, right? So it kind of blocks. This one here is I've got a function that's moving, and this is constant velocity. It's the same regardless. Okay, so this is an object that's moving at a given velocity. All right, so let's go ahead and think about the first case. Okay, in our constant velocity case, what's happening? So I'm gonna just draw this out. So I've got my time, and I actually have velocity on my y-axis, okay? So now, no matter what time it is, my velocity is the same no matter what I'm doing. So if I look at the time interval from t1 to t2, say for example, I've got this sort of rectangular shaped chunk here. Okay, what's happening within this, right? This right here, the area of this is the distance that we've traveled, okay, from time t1 to time t2. This is our delta t from here to here, okay? So let's write this down. So our distance traveled over the interval t1 to t2, which is our delta t. So I would say t2 minus t1 is my delta t, okay? Where that interval is going to be given by velocity times delta t. This is our distance. And this is the area of the rectangle, right? This right here is our base, and this is our height, right? Area of a rectangle is base times height. So base, right, this width, and height is this width, as this measure right there. So that's our height. This measure is our base, okay? So our area is a value, right? It tells us something about the nature of this function. In this case, it tells us about the distance that we've traveled within this time interval, okay? But it's an area. We're calculating the area under this curve between the curve and the x-axis between these two different points on this interval, okay? So if I have a velocity that's changing from interval to interval, what does that look like? Again, I'm going to have my time, my velocity, okay, I'm going to put some numbers on it so we can see. So when I go from time 0 to 2, and I'm at a constant velocity from here to here. When I go from time 2 to 3, I'm at a constant velocity up to here. When I go from time 3 to 6, right, 1, 2, 3, 3 to 6, and I'm going to go from here to here. And when I go from 6 to 8, I'm going from here to here. So again, I'm going to be calculating out the areas of each rectangle. And I'm going to sum up all the areas of those rectangles, right? So if I take a look, right, and I say my delta t is equal to 2. My height is equal to 5. So the area of this rectangle is 5 times 2, which is 10. My delta t is equal to 1. My height is 15, so my area of my rectangle is equal to 15. My delta t is equal to 3. My height is equal to 10. 3 times 10 makes this area 30. My delta t is equal to 2. My height is equal to 5. My area is equal to 10. So the velocity, the total distance traveled from time t equals 0 to time t equals 8 can be calculated by adding up the areas of all these rectangles. right? So if I go from A to B, so if I say A is 0, my B is 8, right? What's the total distance traveled? Right, so I'm going to go, right, delta t times velocity. So I'm going to go 10 plus 15 plus 30 plus 10. And that's going to give me a distance of, let's say, 65 meters. They didn't give you units, but we'll put them in there. Okay, so the total distance traveled from time t equals 0 to t equals 8, I'm just adding up all those areas. Now let's say our velocity is continuously changing. Right, so now what happens? Right, I've got my time, my velocity, right, and let's say my function now looks like this. Here's my velocity function, right? Okay, so now when I want to calculate the area, the total distance traveled, you have to make some decisions. Okay, so on and so forth. I'm going to be adding up the areas of these rectangles here. Okay, I'm still going to be adding up the areas. Okay, so now we'll say our distance traveled. Right, where my base is some kind of delta x. And then the height is going to be my function evaluated at the corner. And how we choose, do I do a left corner, a right corner, or a middle of the rectangle, is going to be what we're going to be talking about today. Okay, so I've got 3 different cases, right? But this is the case that we're going to be focusing on mostly today. Okay. How do we figure that out? You guys good with this here? All right, so let's talk about how we approximate the area by the rectangles. Okay, so approximating area by rectangles, let's talk about it. So the first thing I have to do is I have to choose a whole number. And in our cases, it's going to be given to us. Okay. I'm going to choose a whole number n, and we're going to divide the interval a to b into n subintervals. Okay. We want these to be of equal width. How do we calculate that width, right? So I say my delta x is my width. I'm going to go b minus a, my end of my interval minus my beginning of my interval, divided by the total number of subintervals that I want to have, and leave it as a fraction. Don't round. Don't get a decimal and then round, because you're going to lose some stuff. Okay, leave it as a fraction, but this is really important. Okay. So we're going to talk about doing it with the right-hand edge of the rectangle, with the left-hand edge of the rectangle, and all that. There. Okay. Okay, so if I do the right-hand edge of the rectangle, let's think about it. So let's draw our picture. And I've got my function. Okay, now when I go to do the right-hand edge, so here's my A, that's the beginning, and here's my B, that's the end of my interval. So the right-hand edge, I've got my delta x width. Right-hand edge, that means that that right-hand edge is going to hit my function, and I'm going to make a rectangle that's as wide as that, but it's the right-hand edge that hits my function. Okay, I do another delta x. And I do another delta x. I do another delta x. And then I do another delta x. Okay, you can see how the right-hand edge, right, this dot here, when I'm putting it, is our function, right? So this right here, the height, this is f of a plus delta x. This is f of a plus 2 delta x. This is f of a plus 3 delta x, and so on and so forth. Okay, so we've made these rectangles here. The problem with this, right, as you can see, is that I get this overestimate, this underestimate, 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 overestimate. Okay, but we're going to be dealing with that as we go. But for right now, we're building up the idea that we're going to be taking the area of all these rectangles and we're going to sum it up. So the area under the curve between A and B, okay, from A to B, is going to be the sum of areas of the rectangles from A to B. Okay, so the areas of the rectangle, this is base times height. So our base is delta x, right? And our height is going to be the function evaluated at a plus delta x plus my base delta x times the function of a plus 2 delta x plus my base times the function a plus 3 delta x, and so on and so forth, right up and down to the end, right till I get to the end where I have delta x times f of b, essentially. And I'm going to add all these up, and it's going to give me the area. Okay. So we're going to call this the nth right endpoint approximation. And I'll give you, more specific formula for it. R sub n is our nth right endpoint approximation. Okay. This is our right-hand edge of our rectangle. Right? So we're going to sum up all these areas. The base, delta x, times our function evaluated at the right-hand edge of our rectangle. Okay. Right-hand corner, this area right here, that's our f value. Okay. And let's write down what we have. So we have our interval, which goes from A to B. Our A is our left endpoint of our interval. Our B is our right endpoint of the interval. N is the number of subintervals. On our interval A to B. And then our delta x is B minus A over N. So just a summary. Okay, and then we're going to apply it. Our first example, there's a typo on our first example. I'm going to fix it here real quick. All right, so example number 1, there's a typo. It should be R6 and not R4. Oh, we're also going to do, oh wait, I'm bad. I was right the first time. I was thinking there's a typo on another page. This is right. That was an R4. I'm sorry. I was thinking in the, there's a typo on another page. I was trying to get ahead of myself. So it's R4 and R6. So I was right the first time. Don't correct your page. Okay, so we're going to calculate R4 and R6. This tells us we have 4 subintervals and 6 subintervals, and our function is x squared. And we're going to go from 1 to 3. So I like to graph it out just to kind of visualize. 1, 2, 3. 2, 3, 4, 5, 6, 7, 8, 9. Okay, oops. Okay, so here's our function, right? And we're going to come up with our subintervals for that. So R4, so remember our delta x is going to be b minus a over n. So this is going to be 3 minus 1 over 4. So our delta x to start off with is 1/2. Okay. All right. So I like to calculate out the endpoints ahead of time so I don't have to fiddle with it. I can just plug them into my function and go. So let's figure out our right hand endpoints. Okay, so that's going to look like I'm going to go a plus j delta x, right? So I'm going to start here and I'm going to go there. So I'm going to go a 1 plus j. My first endpoint, I've got 4 of them. So my first one plus delta x plus 1/2. 1 plus 1/2, 3/2. Then I need to start here because I'm going to go from 3/2 to the next delta. So 3/2 plus 1/2 is 4/2, which is equal to 2. Then 2 plus the next delta tells me what's my next endpoint. So 5/2 gives me 2.5. Then 5/2 plus 1/2, that's 6/2, which is equal to 3. When I do the right hand endpoint, my last bit should always be my b, my end. So let's draw our triangles out. So that's going to hit here. So I've got 3, 2.5 here. So this is my, and then here, and then I've got 2, and then I've got 1.5. All right, so here's our function here. Okay, we're going to be summing up the area. Summing up the area of all of those different triangles. Okay, so that's what we're going to be calculating. All right, so let's go ahead and do that. So I'm just making a list. Makes it a little bit easier. All right, so now our rectangles, we have 4 rectangles. Area equals base times the height. So our bases are delta x, that's 1/2. And this is f of a plus j delta x is our height. So I need to sum those up. My delta x is the same for each one, so I'm just going to factor that out. So I'm going to go 1/2 times f of, I'm going to do f of each of these endpoints here. F of 3/2 plus f of 2 plus f of 5/2 plus f of 3. Okay, you need to show this step here, right, in order to get full credit. We're going to be looking for this step. Do you recognize that you're doing base times height? And we're going to add up all those areas. This is how you're calculating the height. Okay, so you have to show this step here. Then you want to show that you're plugging it into your function. So 3/2, our f of x is x squared. So that means I'm going to go 3/2 squared, 2 squared, 5 halves squared, and 3 squared. Okay, I'm going to add all these up. I'm going to divide by 2, and I'm going to get, let's see, what did I get? 43/4, which gave me 10.75. Okay. It was an approximation for the area under the curve, given 4 subintervals. Try it again doing 6. All right, so the first thing I have to do is recalculate my delta x. B minus a over n. 3 minus 1 all over 6 gives me a delta of 1/3. So it's a smaller, I have more subintervals crammed into the same spot. Okay, so my delta x is smaller, which means I need to calculate my right-hand endpoints again. Okay, so we're going to start off with a. So this is 1 plus 1/3, which is 4/3. Then I'm going to go 4/3 plus 1/3, 5/3, 5/3 plus 1/3, 6/3, which is 2, then 2 plus 1/3, 7/3, 7/3 plus 1/3, 8/3, 8/3 plus 1/3, 9/3, which is 3. Let's count it up. We should have 6 endpoints because I have 6 subintervals. I have 1, 2, 3, 4, 5, 6. I have 6 of them. Okay, so these are my endpoints. Okay, and I'm going to plug them into my calculate the areas. 6 rectangles. Area equals base times height. Okay, so this is delta x times our function a plus j delta x. Okay, so we're going to plug them in. We're going to do just like we did before, but now we have a different delta x and we have more of these areas that we have to add up. So my delta x, 1/3 times f of, let's add them, put them all in, 4/3, plus our function evaluated at 5/3, plus our function evaluated at 2, plus our function evaluated at 7/3, plus our function evaluated at 8/3, plus our function evaluated at 3, which is 1/3 time. This is 4/3 squared. Our function is x squared, right? 4/3 squared plus 5/3 squared plus 2 squared plus 7/3 squared, 8/3 squared, and 3 squared. Be very careful when you're doing this on your calculator. Sometimes if I do it all in one long stream, then I make a mistake because I'm not keeping track or I have a typo and I don't realize it. Okay, sometimes it's easier just to do each individual one and then add them up after the fact and then divide by 3 when you're done. I got 271 divided by 27, which gave me approximately 10.037. This should be on the same order as what we found using the method with 4 subintervals. Okay, if you get an answer that's way different, probably made an algebra mistake somewhere. Okay, I'm just going to draw a quick picture while we're thinking about it because I like pictures. 1, 2, 3. Okay, so our endpoints here. So 1, 2, 3, 4, 5, 6. I've got 6 of them. Guess I'm adding up the areas for all of those. Okay, that's what I'm summing up. Okay, that gave me this area 10.037. Okay. This stuff isn't that hard, but it's really tedious. There's just a lot of little pieces that you got to do. Give yourself time when you go to do the homework for this. It isn't hard, but it takes forever because you've got all these little miniature calculations that you have to keep track of. Okay, so keep that in mind when you're doing this stuff. And I'm not kidding when I say it takes a long time just because of all the calculations. But in order to show your work, the work that you need to show absolutely is this line and this line and this line. Okay, you probably also want to show what your delta x is as well. Okay, you have to show those for work. I can tell you for a fact, when you take like a final exam and you don't show your delta x, you don't show this line here where you're doing your base times your height, and you show that you're plugging it into your function. This is f of evaluated that. Then you want to show that you've actually plugged it into your function. Okay, sometimes they'll tell you leave it in terms of e or leave it in terms of pi, depending on the function that you're working with, or sometimes they'll say given number. Okay, but this, and this, and then our delta x is enough for credit. Okay, if you don't show these, you're going to lose points. Okay, just telling you what I've seen when we grade things on the final exam. Okay, all right, let's summarize it using summation notation. Okay, so I use summation notation to write it. So my right hand edge using n subintervals is going to look like my base, delta x, times my heights, j equals 1 to n, f of a plus j, delta x. There's my right hand edge. Okay, let's do our left hand endpoint. So L sub n, it's going to look like, I'll give you the formula, then we'll draw it out. J equals 1, I'm sorry, j equals 0, n minus 1, f of a plus j delta x. Right, so here's our graph. Let's draw out our function. I go from A to B. This is our left-hand edge. So it comes up, so A, right, forms the basis. For that, I'm going to make, here's my delta x. Here's another left-hand edge. That's delta x. Here's another left-hand edge. That's delta x. There's another left-hand edge. That's delta x. I'll try to over-exaggerate here. Oops, I didn't make that very good. Delta x. Okay. This is our left-hand edge. Okay. Okay. Our left endpoint notation, let's do our midpoint approximation. M sub n. Okay. Let's talk about what that's gonna, I'll give you the formula and then we'll draw it out. Delta x times our base times j equals 1 to n f of a plus j minus 1/2 delta x. So now this is a midpoint, so watch what's going to happen. So here's my graph. Here's my function. And I'm going from A to B, right? I've got n subintervals like I have before. And then here's my delta x, but now it's my midpoint, the middle of that forms the basis. So I go delta x, and then delta x, and then delta x. The midpoint is nice because while the right and the left will have over and under estimates, but the midpoint kind of evens out the over and the under estimates. Okay, so we're going to still add up all of our areas of our rectangles, right? So now I want to go from A to J minus delta x, or j minus 1/2. I'm only going to the halfway mark between a and a plus delta x, okay? And that gives us our midpoint. Okay, so you've got your right hand, your left, and your midpoint approximations, okay? All right, so my lecture examples, oh, this is where the typo is. Example 2 has the typo, not example 1. You guys all have that? Okay, let's fix that typo. So it's R6 we're gonna do. R6 and L6 and M6 for the function 1 over x from 2 to 4. I'm just going to, plot it just so I can visualize. Remember, this 1 over x is a rational function. It's got asymptotes at x equals 0, y equals 0. This time we're going to go from 2 to 4. So we're looking at roughly this area right here, okay, on our graph. Okay, so let's start. So I need to calculate, I'm doing 6's, so my n is equal to 6. So my delta x equals b minus a over n. So this is going to be 4 minus 2 over 6. So this is 1/3 equals my delta x. And we're doing R6, L6, and M6. So my delta x will be the same for all three because I don't have to recalculate those values. But my endpoints are going to change for each one. All right, so let's start off. R6. All right, let's remember delta x times j equals 1 to 6 f of a 2 plus j delta x. So I'm going to write in 1/3 times the sum j equals 1 to 6 f of 2 plus j times 1/3. Okay. So this is my base times the sum of my heights. Base times height plus base times height plus base times height. We factored out the base because it's the same each time. All right, so let's go ahead and do it. So 1/3 times f of 2 plus 1/3 plus f of 2 plus 2 times 1/3 plus f of 2 plus 3 times 1/3 plus f of 2 plus 4 times 1/3. You get the idea about how it can be tedious. 2 plus 5 times 1/3. 2 plus 6 times 1/3. Okay, so let's calculate what these are. So this is 1/3 times f of 7/3 plus f of 8/3 plus f of 9/3, which is 3, plus f of 10/3, f of 11/3, plus f of 12/3, which is 4. Okay, remember our function is 1 over x, right? So I'm going to substitute that in. So it's going to be 1/3 times 1 over 7/3. I put the parentheses on it because when you do this in your calculator, if you go 1 divided by 7/3, it may not get the order of operations right, depending on how your calculator does it. Mine won't, unless I do parentheses. Okay, so make sure you've got parentheses and you watch out for your calculators. Plus 1/3 plus 1 over. Okay, I plugged it into the function, right? What I see is a common mistake. People get this part right, f of 7/3 plus f of 8/3, and then they add up 7/3 plus 8/3 plus 10. Okay, so be very careful. You're plugging it into the function. So our function is 1 over x. This becomes 1 over 7/3. Okay, so I'm going to add all these up, and I'm going to get this was approximately equals 0.653. That was for our right hand using 6 subintervals. Okay, we're going to do it now for our left hand using 6 subintervals. So our delta x doesn't change. Okay, but our f of values will change because we're using the left hand. All right, so L6 is going to equal, let's write that down, j equals 0 to n minus 1 f of a plus j delta x. So delta x, 1/3, j equals 0 to 5, n minus 1 is 5, f of 2 plus j times 1/3. Okay, base times height. All right, let's do it. So 1/3 times f of 2 plus 0 times 1/3. F of 2 plus 1/3 plus f of 2 plus 2/3 plus f of 2 plus 3/3. All right, it is 3/3, you can see it, plus f of 2 plus 4/3 plus f of 2 plus 5/3. Let's just check. 1, 2, 3, 4, 5, 6. I have 6 of them, which I should, because I said we're going to do 6 subintervals. Okay. All right, so let's go ahead and do it. So this is going to be 1/3 times f of 2 plus f of 7/3 plus f of 8/3 plus f of 9/3 plus f of 10/3 f of 11/3, which is equal to, I'm going to plug it into the function now. 1 over x, 1 over 2 plus 1 over 7/3 plus 1 over 8/3 plus 1 over 3 plus 1 over 10/3 plus 1 over 11/3. Okay, I'm going to get a number. That was approximately equals 0.737. It's on the same order as 0.653, right? If I got 7.37, I think I probably made a math mistake somewhere. They should be close, okay? Not too far apart, along the same order. Whew. Right? It's a lot of work, a lot of writing, and just kind of tedious. So give yourself time when you're doing these problems. Okay? All right, let's do the middle. The midpoint. Okay, so M6. M6 is delta x times j equals 1 to n, f of a plus j minus 1/2 times delta x, which is equal to 1/3, that's our delta x, times the sum j equals 1 to 6, f of 2 plus j minus 1/2 times 1/3. Okay, so we're going to start plugging these things in. You ready? 1/3 times f of 2 plus 1 minus 1/2 times 1/3 plus f of 2 plus 2 minus 1/2 times 1/3 plus f of 2 plus 3 minus 1/2 times 1/3 plus f of 2 plus 4 minus 1/2 times 1/3 plus f of 2 plus 5 minus 1/2, and then 6 minus 1/2 times 1/3. All right, let's do it. 1/3 times f of, so this is 2 plus, I'll give you a little intermediate step, plus f of 2 plus 1/2. Oops, 2 plus, sorry, 2 plus 3 halves. 1, 2, 3, 4, 5, I missed one. 2 plus 1, 6, 2 plus 1/2, 5, 6, 7, 6, oh yeah, and then f of 2 plus 11, 6. Okay. One, 2, 3, 4, 5, 6. Okay, good. All right. Okay, so I'm going to plug it into my function. So this is 1 over x. So this becomes 1 over 13/6, 1 over 15/6, 1 over 17/6, 1 over 19, 6, 1 over 21, 6, 1 over 23, 6. Oops, sorry, 1 over. Okay. And that gave me approximately 0.692. Midpoint's going to be closer to your actual area under your curve because it minimizes the error, the over and the under estimates. Okay, it's tedious, right? There's a lot of stuff. I'll let you guys finish writing that and then we'll move on. You guys good? Okay. All right, so let's think about it. So we go to compute the area. We want to think about, right, we talked about, well, if I add more, like if I only have 4 rectangles, right, I get an approximation. If I increase that to like 8, I get a better approximation. If I increase that to like 800, I get an even better. If I increase that to like 8 million rectangles, I get a really, really good approximation. So if we think about the area as the limit of approximations, we can do a lot, right? We can actually come quite close to figuring out what the actual area is in the curve, under the curve. So let's think about that. So I'm going to do, we want to increase the number of rectangles in the same interval, right? So we're going to go, n's going to go to infinity, right? Delta x, right, gets smaller, okay? But a to b is the same, okay? A to b is the same. So we're going to increase the number of rectangles in the same interval, okay? It's going to give us a better approximation of the area under the curve. So the area between the curve and the x-axis is really what we mean. So let's do a couple examples. So here's, right? So let's say here's my function. Right, so I'm going to go right. So I've got this here. Now think about it, right? I've got this, the error that I'm dealing with is this bit right here, this yellow bit. Okay, that's my error, right? I've got this, all this extra stuff. What I really want is just the area between the red and my x-axis. But I've got all this over approximation. So I'm going to increase the number of rectangles. You can imagine. Right, and make the delta x smaller. I increase the number of rectangles. I keep my interval the same. And I'm just showing, you know, the right-hand edge here, but right, so take a look. Right now, this little bit right here, that's our area, that's our error in approximation. We've overestimated our area by just that amount. It's a lot smaller than this area here. Now imagine, right, so here's our function. Right, so imagine now, if I made my rectangles infinitely thin, okay, I'm just going to draw them out like lines so you can see them, but infinitely thin rectangles, and I take their areas. I'm going to draw them with spaces so that you can see them, but imagine I do that and I just keep, you know, I have an infinitely thin rectangle and I have an infinite amount of them in the same interval, right? My error of over approximation or under approximation is going to go down to 0, right? But it's hard to do an infinite number of rectangles unless I think about it as a limit. Okay, so this is basically n is going to infinity. Our delta x is going to 0. Okay, in the same interval. Okay. So this is our picture. I'm going to write it as a theorem. Okay, and then we're going to actually start working through some stuff. You guys all have this, okay? Okay, so if our function is continuous on an interval a to b, then the endpoint and midpoint approximations, so this is our right and our left, and our midpoint approximations approach the same number. Right, this is our limit number. Approach the same number as n approaches infinity. So we're going to go like this. I'm going to take the limit as n approaches infinity of my right hand. That's going to be equal to the limit as n approaches infinity of my left hand, which is equal to the limit as n approaches infinity of my midpoint. And that's equal to some value, whatever that is, right? Whatever that limit evaluates to. But basically, we're approaching the same value, okay, as n goes to infinity. Which is the area under the graph of our function from a to b. Okay, and now we're talking about functions that are greater than or equal to 0. We're going to talk about functions that go below the x-axis at some other time, but not right now. Okay, in order to evaluate these limits, we're going to need what's called a power sum. We kind of hinted at this yesterday, but let me just give you what the summations are on these things. So say, for example, if I'm summing up j equals 1 to n, I'm just going to sum up j. So this is like 1 plus 2 plus 3 plus all the way up to n, right? Especially as n goes to infinity. I don't want to do this forever. This is going to be n times n plus 1 all over 2. We're going to use these formulas here when we calculate our limit. J squared. So this is like 1 squared plus 2 squared plus 3 squared plus n squared. So that's going to equal to n plus 1. Oops, sorry, 2n plus 1 divided by 6. And then if I sum j equals 1 to n, j cubed, so 1 cubed plus 2 cubed plus 3 cubed plus n cubed. This is going to give me n squared, n plus 1 squared all over 4. These are formulas, right? So I don't have to sit there and calculate what is it equal to. I just use the formula, and I'm going to need that for when I actually calculate things with a limit, like we're going to do in our last example. We're probably going to get through only like the first part of this example, and then we'll finish it on Monday. But let's go ahead and get started on that. All right, so I want to find the area under the graph f of x equals x from 0 to 4, and we're going to use geometry. We're going to use the limit as n goes to infinity of r sub n, and we're going to use the limit as n goes to infinity of L sub n. Okay. When we say geometry, the geometry is just to show us you can't use geometry on an exam. 1, 2, 3, 4. Geometry is just for us to see, to confirm, because this forms a triangle, a right triangle. So for part A, the area of the triangle is 1/2 base times height. So 1/2, my base is 4 units, and my height is 4 units. So this area here is equal to 8. We're going to use that just as a basis of comparison for when we do our limits, okay? But like I said, you can't use the geometry on an exam. Okay, so now the limit as n goes to infinity of r sub n. Okay, so we don't know what n is, right? N's going to go to infinity. So I'm not giving you a number, so I can't calculate delta x. So all these things, right? So I have to be able to come up with a formula for r sub n in order to figure out what things are. So let's think about it. Let's take a step back. So when we calculate delta x, we say b minus a over n. So this is going to be 4 minus 0 all over n. So delta x is 4 over n. We're going to do all these things in terms of formulas, right? In terms of n. Okay, we're doing r sub n. During r sub n, so we want to be able to think about what the formula is for r sub n. Let's remember delta x times the sum j equals 1 to n f of a plus j delta x. Okay. All right, let's start putting things together. So let me think about that one. So f of a plus j delta x. This is going to be a is 0, so this is f of 0 plus j delta x. So this is f of delta x. This is going to be j 4 over n. Okay. If my function f of x equals x, the thing the height, I'm going to take this j over 4 and plug it into x. The height's just going to be j 4 over n. So this, I'm going to sum up all those heights. I'm going to be summing up j 4 times 4 over n. All right, so let's put it together because we have to come up with a formula now, right? I don't have a value for n. I can't come up with an actual number. I have to come up with a formula and evaluate the limit. All right, so r sub n. So delta x. So this is going to be 4 over n, right? So it's my delta x times j equals 1 to n of f of a plus j, right? So this was f of j plus 4 over n. F of x equals x. So therefore, f of that is just j times 4 over n. Now, let's do a couple things. Let's talk about this one, right? My index is with respect to j, right? So j is the thing I'm going to be summing. So that means that this is a constant term that I can factor out. Okay, so I'm going to rewrite this. So this is going to equal 4 over n from before times 4 over n that I've just factored out times j equals 1 to n of j, which is 16 over n squared, j equals 1 to n times j. So this, right, remember we just did that. It's one of our power sums, right? If I sum from 1 to n, 1 plus 2 plus 3 plus 4, or whatever, I can substitute in. I don't have to do the summation anymore. I can substitute in what that power sum was. So that power sum is going to be 16 over n squared times n plus 1 all over 2. Right? That comes from our power sum. Okay. We just substituted that. Now I can clean this up, right? The n and the n squared, the 2 and the 16. So the r sub n is r sub n is 8 all over n times n plus 1. Okay, which if I distribute the 8 over n to each term, I'm going to get 8 plus 1 over n, r sub n. So let's take the limit of that. So the limit as n goes to infinity of r sub n is equal to limit as n goes to infinity of 8 plus 1 over n, right? This right here, this goes to 0. You have to show that, which is equal to 8, which is what we got when we did the geometry, right? Okay. We're going to do the same thing for the L. Okay, but what we'll do is we'll finish up the L next time. We'll do that when we start next time. Okay, I don't want to rush it. We only have 5 minutes left to the end of class. I don't want to rush that. Okay, guys? Watch out. This stuff can be really tedious. There's like a lot of little pieces that you have to keep track of. Okay, and a lot of bits and pieces that you have to add together. But it's giving you an idea when we talk about when I take an integral from A to B, the area under the curve, we're summing up all these like little rectangles, right? And we want to make an infinite number of rectangles. We want them to be infinitely thin, right? So the area under that curve is a really good number, really good approximation, right? So this is the background for our definite integral. Okay. Phew, a lot of work. We'll come back to this next time on Monday. Okay, don't forget we have a quiz today, guys. So that's going to open up at noon today. All right, you guys take care. Have a good weekend.
Thank you.
Bye.
Thank you.
Bye. Take care.